So I want to talk about London equations. Typically people don't teach these things anymore, but I think the book is doing a good job to introduce these things. To me, the London approach to superconductivity is kind of like Bohr approach to atomic physics, right? So when the atomic physics was being built, and there were all kind of problems, and there were no quantum to work with, right? The quantum mechanics as we know today was non-existent. But the genius of Bohr, for example, this is what Einstein says, was that he could be able to get out quantum result from classical mechanics, right? That's like, even without knowing quantum mechanics, he could get out quantum mechanics. And London equations, not in the same class of Bohr model, of course, but I think it is kind of like that. It is also doing quantum mechanics without doing quantum mechanics, as we are going to see. And it's, I think, good to know these things in research. So our goal is to explain superconductivity and Meissner effect and things like that. But London, actually, this is one London, but there are actually two of these, London and London, two brothers. They started from classical physics and classical conductivity. Let's consider AC conductivity, which is more general and more applicable to our case. So the Newton equation is m dv dt plus m over tau, this is the direct force, is equal to minus E. And in the case of AC conductivity, like a easy way to calculate things is like do this complex representation. E is complex and V is some, if you want, V of omega times e to the minus I omega. And we substitute here. If you substitute here, what you are going to find is minus I omega m dv dt e to the minus I omega t plus m over tau v, I think I already took the derivative, so there is no derivative here, e to the minus I omega t is equal to minus e to the minus I omega t. So we cancel now exponents and find v minus e, I think this is tau here, and divided by m 1 over 1 minus I omega tau. But I didn't do anything, I just solved this for v. And this I'll substitute in the, yes. Oh, yes, absolutely. So let me, thank you. So this is, and j is equal to, so as a vector, minus e and v, and it is going to give us e squared tau n divided by m 1 minus I omega tau times e, and this defines frequency dependent conductivity. If you want, this is also the root model, but in frequency dependent form. Good. Now, this thing you can see has like real part and imaginary part, and real part is the dissipative component, and imaginary part is so-called inductive component. Let's look at the real part. E squared tau n over m 1 over 1 plus omega squared tau squared, and I like to write tau to here, and you can see this object is exactly like a Lorentzian. The width is 1 over tau and height is tau. Let's think about this integral minus infinity to plus infinity d omega real sigma of omega is equal to e squared n over m minus infinity to plus infinity d omega tau over 1 plus omega squared over tau squared. And this integral can be taken at standard arctangent e squared n over m times pi. So for a perfect conductor, tau to the minus 1 is going to go to 0. There will be no scattering. And sigma of omega in that limit is going to be 1 over minus I omega e squared n over m. I didn't do anything. I just put tau goes to 0 limit of this thing and or this thing, and it gave me a purely imaginary conductivity, and we can see this is inductive component. That means there is no dissipation, and that's what we should have because we said scattering goes to 0. But the integral, as you can see, we integrated this thing and there is no tau, and in that limit this thing needs to be conserved. That's why we sometimes call this sum rule. But integral should be conserved as tau inverse goes to 0, and you can see as tau inverse goes to 0, this thing is going to go to Dirac delta, and from here what we conclude is real sigma of omega should be this e squared n over m pi. It's 0 everywhere, but there is like a Dirac delta component. So this is a result. Now let's come to London and London considered a two-fluid model, fluid exactly like in helium-4, and that's what actually they were inspired. And they said total density is n normal plus n super, and they considered this super component to be like a perfect metal, and that's so this one is similar to tau inverse goes to 0, exactly like what we derived. And they considered this sigma of omega to be e squared. Now they put ns, this superfluid density, divided by mass times pi delta of omega minus 1 over I omega e squared ns over m. And incidentally, if you look at the experiments, So this is the experimental result. This is sigma of omega. This is omega. Actually, this is, let's draw the real part of sigma of omega. There is indeed, so this is the experiment. There is indeed like a peak in the center, zero frequency component, exactly like London suggested. But the difference was there was like this delta over h bar. If you want, this is minus, this is plus delta over h bar, and it goes like that. So we'll see. So this here is gap, and this gap we are going to explain it with BCS theory later. But of course, London didn't know about that. So their theory was valid for this zero frequency component. So let's see what they did. So what they did is like, so this, let's write J e to the minus I omega t is equal to sigma of omega, exactly like Ohm's law, but frequency dependent, e to the minus I omega tau. And so let's take the curl. If you take the curl, you have del curl j e to the minus I omega tau is equal to, so I want to write it like this. Let me write it in two steps. So this is del curl of, actually I want to write it like this, curl of e to the minus I omega t, so this full component, and this is curl of e, and we know curl of e here is minus del b del t from Maxwell equations, and we are saying b, if e is e to the minus I omega, b is e to the minus I omega t2, like exactly the same form. And from here, what we obtain is I omega, and let's put also this minus 1 over I omega, what we derived earlier, e squared and s over m. So this is tau inverse goes to zero limits of frequency dependent conductivity times b e to the minus I omega t. Now here we can now take the omega goes to zero limit of this equation, and what we find is, okay, this I omega and this cancel. What we find is del curl of j is equal to minus e squared and s over m times b. Good. And now I can use Maxwell, right? So this is j and this is b, and Maxwell says curl of b is equal to nu zero times j. Or I can take curl of both sides. Curl b is equal to nu zero curl of j, and curl of j from this equation is minus b. Then what I find is curl of b is equal to something like minus, let me define this, lambda squared b, and lambda, so lambda squared is equal to, actually let me write lambda root m over e squared and s mu zero. Okay. And this is sometimes what we call penetration depth. And what this equation says, like we can think about like a simple geometry, and right. So you can, for example, open this up, del dot b minus del squared b, and del dot b is always 0. So you have Laplacian of b is equal to b, and we can think about solving this equation in simplest geometry. And simplest geometry is we have, say, something like that. This is x, and here there is like, if you want, this is x is equal to 0. I can have normal metal here, and I can have this b is equal to constant. And from this equation inside the superconductor, there is like a boundary condition here, and it should decay like exponentially. Right? And this decay length is lambda. So this equation tells us whenever you turn on B inside superconductor decays. And the decay length is given by these microscopic parameters. So this is B of x is equal to some B0 times e to the minus x over lambda. Good. So that's how we explain the Meissner effect. Now let's consider, or like let's use B is equal to curl A. Then, and also let's use this equation we just derived is equal to minus e squared ns over m. It was B, so let me write it, curl of A. And from here we have J is equal to minus e squared ns over m times vector potential. So this is London equation. But we know A goes to A plus a gradient chi, right? There's like this gauge invariance, and by using also continuity equation, del rho del t plus del dot j is equal to 0. And I want to look at DC limit, and there is no charge. In that case, del dot j is equal to 0, and which means, right, from this equation, del dot a is equal to 0, right? And this is what we call London gauge. So this equation, there's also gradient term.
In J proportional to A, can you also have like a gradient term?
Yes, this is that's how I fix. I fixed the I got rid of that extra term by taking the London gauge. Good. Now we have, as you can see, a new length scale lambda. Previously, okay, let's go through the length scales. Length scales in a superconductor. Previously, we were talking about impurity scattering, right? There was, from this Drude result, we had like a scattering time, or from this scattering time, we can define like a length, which is called mean free path, and this is defined by Fermi velocity times tau. So this is mean free path. This is like a sample specific quantity. Take any substance, it has its own mean free path, which can be determined from the conductivity residual conductivity at low temperatures. So this is one scale. Now we also had introduced this lambda penetration depth. This is the second length scale. And a third scale that I have to give you a hint is so-called coherence length. Xi 0 is defined by h bar V Fermi divided by pi times delta, this superconducting gap. So this is so-called superconducting coherence length. If you want, this is kind of like size of Cooper pair. So BCS theory explains superconductivity by electrons being paired. When they pair, they are bosons, and those bosons can Bose-Einstein condensate. But you'll see it is a completely different kind of condensate. That's why we cannot call it Bose-Einstein condensate. But this pair has like a characteristic length given by this. And in the coming lectures, we are going to see kappa defined by lambda over xi naught will determine whether we have type 1 or type 2. So we are going to do this within so-called Ginzburg-Landau formalism. And we'll see how kappa determines which type of superconductor is. Another thing is like if L is much larger than this Cooper pair size, this is clean limit. And in that case, we understand why superconductivity survives. But in the opposite case, if L much smaller than xi naught, so this is what we call dirty limit. And interestingly, many superconductors, and this is also one of the reasons why this phase of matter is so robust, many superconductors are robust in that limit. Okay? It's like a curious thing at the moment, but I don't know if we can talk about this, but this has to do with so-called Anderson theorem. Hopefully we can talk about it at some point. Good. And the reason I introduced all of these things because lambda came up and we already have L. Now we are in a position to look at this thing from like a broader perspective. If you are not tired, I have like maybe 1 page of calculation and I will finish it. And I'll just show you how London equation gives rise to vortex, and that vortex is going to be exactly like the vortex we introduced for superfluid helium. And it's going to complete the analogy, and then we can call it a day. Good? Let's talk about London vortex. This is kind of like your exercise from last week, but applied to superconductors. So we obtained del cross B is equal to minus 1 over lambda squared B. And like I said, I write this like del dot B minus del Laplacian B. And this one is 0 because there is no magnetic monopole. By the way, this is, if you want to see the details about this, you can look exercise 3.3 from the book, James Annett. Therefore, the equation we need to solve is del squared B is equal to minus 1 over lambda squared B. Yes, but each component, right? This is component by component. But here what I want to consider is, like I want to consider, because I want to look at the vortex, I want to consider like a 2D vortex with cylindrical symmetry.
It should be plus.
Is it plus? Yes. I think this is, yes, it is plus. Thank you. So this is cylindrical symmetry. What I mean is we have this, if you want 2D system, maybe the width is not very important, but and here I want to put a vortex like this, and I want to have this rotational symmetry, two-dimensional rotational symmetry. In that case, so this B vector is going to be some B which may depend on R, but its direction is going to be Z, and all other components are going to be 0, right? The only B is going to be along here. And I can open that Laplacian. If you open the Laplacian, what you have is 1 over R d dr r d. So this B, the dB dr is equal to 1 over lambda squared B. So now this is not a vector anymore, right? I took out the vector component. And now I can think about this vortex, the physics of this vortex. So if you zoom in, to a vortex, here are the length scales. So here's the center of the vortex, and there's like a region where this thing is empty, right? If you look at the vortex, you are going to see a hole, and the size of this hole is order of this Cooper pair. And there is going to be a region where there is like a magnetic field, so there is going to be order of lambda. And if you go beyond lambda, right, magnetic field decayed exponentially here. Beyond here, there will be B is equal to 0. So that's the physics. And to understand the vortex, we can think about this regime, right? This psi of 0 smaller than r, and let this be much smaller than lambda. So in that regime, lambda is much larger, so 1 over lambda is much smaller, so I can drop this term. So drop 1 over lambda squared term, because 1 over lambda is big. In that case, I have 1 over r d dr r dB dr is 0. And this means r dB dr is some constant, let me call this a, and this can be solved, right? Just take this to here and integrate both sides. B is equal to a times ln r plus another constant b. And from this b, right, we can look at the corresponding current. So corresponding, so there is like a b here coming out of page, but there is like circulations around this vortex, and we want to find these circulations by calculating corresponding current. And so del cross B is equal to mu 0 J. So this is Maxwell equation. And exactly like what we did for superfluid helium, I want to write this. So this is ER, R, E phi. So this is phi. So this is EZ. So this is del R, del phi, and this is del Z. So this component is 0, this component is 0, and we only have B of R here. And so this B of R is this thing. And from here, right, you can just, almost everything is 0. You can just calculate J and find it to be minus A over nu 0, 1 over R E phi. Okay. So compare with helium-4. I think we calculate something like this for helium-4. And what this means is like exactly in the case of helium-4, we have these superflows like this. And there is like this decaying magnetic field, and there is like a vortex core, right? So this is, if you want, B. So this is R, and in that case, core is chi 0, decay length is lambda. Okay, like I have one last line of calculation, and then after that I'll finish. If I have A from the London equation, if I have J from the London equation, I have vector potential, and vector potential is minus m over E squared ns times J, and that means this thing is equal to minus A, let me write it in terms of lambda squared, A lambda squared 1 over R E phi minus A lambda squared. So I just rewrote this thing and I wrote the definition of lambda squared here. Now what I want to do is I want to take integral and calculate the flux. So this is B dot ds, and I can use the Stokes theorem. Okay, there is, I think there is like a minus, but never mind. I can use the Stokes theorem here and write this like A dot dr. And now I look at this and here, and I look at here, and this integral can be taken. This is going to be minus A lambda squared 1 over R times 2 pi R, and cancel R, and from here we can see that this integration constant is fixed by flux, and it is going to be 2 pi lambda squared. Later, like I said, we are going to see this is going to be h over 2e squared, and this b of r, in that case, is flux divided by 2 pi lambda squared ln lambda over r. Good? Any questions? Okay. I think this is pretty much exactly the same calculation we did for superfluid helium, but for superconductor. That's the message. All right. Thank you.
Vortex,
What's that?
when we talk about vortex, do we have some distance between the, like, actually, what we see is it's a point at the center of the wave.
Yes.
Vortex, but does this vortex any radius or?
Yes. Like so inside. So like it depends on what you define with vortex, right? Let's draw how it looks from the top. Suppose we are looking at like a disk sample, and so first there is like inside there is like a region which is hollow, right? Here there is nothing, right? This is empty, and here B is constant. There's like a magnetic field, and the size, the radius of this hollow region is psi naught. Now there is a second radius where B is non-zero, but it decays exponentially, and this radius is given by lambda. And if you go beyond this lambda, B is 0, and you have bulk superconductor. B is completely expelled. So that's the picture of vortex.
And
So,
for understand the radius of this vortex, we need to look at Cooper.
So if you think, there are different radiuses. In some problems, the radius could be like psi naught, Cooper pair size, but in some other problems, it could be lambda 2. So the vortex size depends on what you mean by that, right? Because we have two different length scales, and some problems are going to be coupling to psi naught, some problems are going to be lambda. So what you mean by vortex radius depends on how you look at it. Good. Right. Thank you.